This is what I want to do now, right? I want to show you something. So let's say we have the numbers. So again, let me just list this out here. We said that 2, 3, 5, 7, and 11 are our prime numbers because the factors are 1 and itself. So 1 times 3, 1 times 5, 1 times 7, 1 times 11. Right? So these are prime numbers. Then if you look at your composite number 16, the reason we said that this is a composite number is because there's more than just two factors that can make up this number 16. Right? Like 1 times 16, 2 times 8, 4 times 4. So there's 6 factors that can, when multiplied together, can give you 16. And remember, there's so many other possibilities, like C8 can further be simplified as 4 times 2. So therefore, we can say that there's so many different possibilities when multiplied together that can give you 16. Okay? Now, this is what I want to show you. You see in maths, I think I've stated this in the previous video. There's only two things that we do in maths. We simplify and we solve. Right? We simplify or we solve. That's the only two things that we do in maths. And I said that whenever you're simplifying, right? Whenever you're simplifying, you're going to make sure that you do it in the fastest, best, right? And in the simplest way possible. Because if you can do it in this way, yeah, then you basically are working efficiently because you understand a more rigid approach to get to the answer, right? You're not just working based off complex ideas. Because remember, our aim in maths is to analyze. This is what you will learn this word a lot. Analyze means you're trying to break something complex into smaller, manageable sizes so that you can make it simple, so that you can get to an answer. This is what we are doing. We're trying to analyze a problem, right? So we're starting from something complex, breaking it down to simpler parts so that we can get to the answer, right? So basically, from all of this here, everything that I've just stated here, you can see that it's quite clear that if you look at 16, right? Looking at 16 can be represented in two ways. And this is what we have. This is why we talk about prime and composite numbers. It can be represented as a product of prime numbers, or it can be represented as a product of composite numbers, right? If it's represented as a product of prime numbers, then it'll be 2 times 2 times 2 times 2, right? But if I represent it as a product of composite numbers, then it could be 1 times 16, or 2 times 8, or 4 times 4, or 2 times 4 times 2, right? Or 1 times 8 times 2. Do you understand what I'm saying? There's so many different possibilities that could give you 16 if you're using composite numbers. But if you're using prime numbers, there's only one possibility. Why? Why is it that when I'm using prime numbers, there's only one way that I can represent a number if I use prime numbers? But if I use composite numbers, the product of composite numbers, to give you 16, there is multiple ways. Why is that? Why is that the case? The answer is very, very simple. Very simple. Watch here. You see with prime numbers are irreducible. It's in the simplest form, right? Simplest form. And it's very unique. Very, very unique. Right? What do I mean by that? If I look at 2 can only be a result of 1 times 2. It cannot be a result of a product of any other two numbers. 3 can only be the result of 1 times 3. It cannot be the result of a product of any other two numbers. 5 can be only represented as 1 times 5. 7 can only be represented as 1 times 7. 11 can only be represented as 1 times 11. Why? By definition. Because the definition states that these numbers can only be represented as a product of 1 and itself. Let me repeat that. These numbers are unique because we said that prime numbers can only be represented as a product of 1 and itself. However, with composite numbers, there are multiple ways of representing a composite number because there are many factors that can make up the number by the definition. So if you're taking a number and you're expressing it as a product of composite numbers, see 8 is a composite number here. If I'm expressing it as a product of composite numbers, even here to composite prime and composite numbers, you're not getting it into the simplest form. Because imagine, think about this. Think about this. If you represented some number with only prime numbers, then you know every number here is in its simplest form because each number is unique. However, if you represented this number here as a product of prime and composite numbers, then the composite numbers in that product can be further simplified. Like, let's look at this example here. See, 2 times 8 is one way of representing 16 using composite and prime numbers. But see, because you have this composite number here, 8, it can further be simplified down as 2 times 4 times 2. And because you have this composite number 4, it can further be simplified down into 2 times 2 times 2 times 2. And now can you further simplify this down? No, this is in the most purest form. It's in the this is why we say it's irreducible. You cannot reduce this further because each number here is a prime number, and by definition, prime numbers can only be represented as a product of two numbers, one and itself. So therefore, what I'm saying is that if you're using prime numbers to represent a number, then you can rest assured that that product is in its simplest form. Okay? Therefore, what we can say is that composite numbers, according to the definition of composite numbers, are the following. It's reducible. If you have a composite number in the product, you can further reduce that. You can also conclude that it's not in the simplest form, right? So it's complex because you can further simplify it down, and it's not unique, right? So this is what I want to do. Now, why am I teaching you this? Why am I saying this? Because let's say that I have two numbers. Let's say that I have two numbers like 16 and 32. If I represent 16 with prime numbers, we just said it can be 2 times 2 times 2 times 2. If I represent it with composite numbers, it's 1 times 16, 2 times 8, 4 times 4, and all of the other possibilities. If I represent 32 with prime numbers, it'll be 2 times 2 times 2 times 2 times 2. If I represent it with composite numbers, it'll be 1 times 32, 2 times 16, 4 times 8, right? And no, so that's basically where it stops, right? So if I'm looking at these two numbers, if I represented them with prime numbers, there's only one way that I represented them each with prime numbers. But if I represented them with composite numbers, there's three possibilities, and I didn't even list all of the possibilities. These are just basically some of the ways. I can still go again and further simplify this here as 2 times 4 times 2. And I can still go further simplify this here as 2 times 2 times 2 times 2. What's the significance of this? The significance of this is if I'm trying to compare these two numbers, 16 and 32, right? And I just said now you can have prime, composite, prime, and composite. If I'm trying to compare these two numbers, I can say, looking at it from the perspective of prime numbers, so looking at it from this representation here and this representation here, I can say something. Looking at it from this perspective, I can say that 32 has one extra factor of 2. Think about that. Because 16 has how many factors of 2? 4. 32 has how many factors? 5. So it has one extra factor of 2. But that's not the point. I'm going to lead this to some other topic. But the idea that I'm trying to say here is, if you looked at composite numbers, you cannot compare these two numbers using composite numbers. Because there's so many different possibilities. Which of these three possibilities are you going to use for the comparison? And then how many comparisons can you make? You can compare this way, this representation with either of these three, this representation with either of the three, and this representation with either of that three. So therefore, what I'm saying is, when you're using prime numbers to compare numbers, it's much more convenient because there's only one way that you can represent them. And why is there only one way? Because prime numbers themselves are irreducible, it's in the simplest form, and it is unique. However, if you're using composite numbers to compare numbers, for example, if I express this as a product of composite and prime numbers, then there's so many different possibilities that you could get. And it's basically more complex for you to actually compare these numbers. Okay? And so take this down. Right? Take this down. And this is the significance of prime numbers. This leads to our discussion on prime factorization. So prime factorization, again, what is a factor? A factor is a number that is divisible that can divide into another number evenly. So prime factorization is basically taking some number and expressing it as a product of prime numbers. So how many prime numbers, or the product of what prime numbers will divide evenly into that number, into that given number. right? So I want you to write this down. Prime numbers are crucial in mathematics because they are the building blocks of all natural numbers, specifically composite numbers. So prime numbers are crucial in mathematics because they are the building blocks of all natural numbers, more specifically our composite numbers. So if you look at any composite number, even 1000, it can be expressed in the simplest form using prime numbers. So 1000 can be represented in many ways using composite numbers and prime numbers. So you can find them in many different ways if you put them as a product of composite and prime numbers. However, if you express it as a product of only prime numbers, that will be the simplest way of representing it. Okay, so that's the reason why we say that it's the building blocks of all numbers, because all composite numbers, because it's the simplest way of representing them. Okay, write this down. Every composite number can be expressed as a product of prime numbers. Every composite number can be expressed as a product of prime numbers, which is known as prime factorization. Since prime numbers themselves are in their simplest form, using them to represent composite numbers helps us to compare them. This is exactly what I just explained here with these two numbers. I said that since prime numbers themselves are in the simplest form, using them to represent what numbers? Composite numbers, helps us to compare them. So now we can compare them more easily because there's only one way of representing any number using prime numbers. So therefore I can compare them now because there's only one way of representing them. There's not like the multiple possibilities as we see on this or using composite numbers. Okay, so it is the best way to compare them, right? And again, like I said, it goes back to the whole idea that we're trying to compare these numbers we're trying to simplify these problems in the fastest, best, and simplest way possible, right? So you will see the significance of prime numbers and prime factorization when we start talking about LCM, HCF, exponents, factorization, and fractions. But for now, that's basically what I want to say, right? So if you look at it from a different perspective, it's similar to saying your prime numbers are like atoms, right? It's like atoms. It's like the building blocks of life, and your composite numbers are like your chemicals. So if you look at the human body, it's so complex to actually understand. Right? If you just look at the human body, it's such a complex machine. If you have to think about it, right? There's so many things happening simultaneously. However, if we break it down into the more simplest form, like your atoms, then we can start drawing conclusions about interactions between different moving parts. Because if everything is represented in their simplest form, then I can start comparing them because I know it's in the simplest form. But if I start comparing them when it's already so complicated, how can you draw a conclusion? How can you actually derive anything when it's such a complicated machine already? And this complicated machine is made up of more complicated parts. So you need to take every part, each bit of it, like the heart and the brain, and break it down into its simplest form, like with the atoms, so that we can understand how they interact with each other and what's common and what's different. If you look at the heart as it is, and if you look at the brain as it is, it's very difficult to actually draw conclusions about how they interact and how it actually functions, because those are just two complicated parts on its own. So that's basically what I'm trying to say, is why we're using prime numbers, because if prime numbers are in the simplest form, using them to represent something else that is complicated helps us to compare them and derive conclusions, because I can rest assured that this is in its simplest form and that is in its simplest form, because we are using prime numbers which themselves are irreducible, in the simplest form, and unique. Okay, and I promise you, you have to understand this now, because there's a grade 12 problem, exponent problem, that where we will utilize this idea, right? The whole idea of numbers being unique. Again, I said that 2 can only be a product of 1 and 2. 3 can only be a product of 1 and 3. 5 can only be a product of 1 and 5. Okay, just remember that. This is very important. This is why I brought this whole idea of it being unique. However, 16 can be a product of many possibilities. 1 and 16, 2 and 8, 4 and 4. Right, so there's many possibilities that could give me that composite number 16. Okay, but when you're looking at prime numbers, there's only one possibility. Okay, so yes, so that's basically what I want to discuss in this topic. Now we can move on to LCM and HCF. So yeah, so this is where the multiples and the factors definition will come in.